All right, let's get started. Apologies if my voice is a little off. I thought it would be a good idea to develop like an upper respiratory infection over Thanksgiving break. So, hope everybody had a better break than I did, though. Okay, so a couple of brief announcements, and then I'll cover some housekeeping to wrap this class up because we are pretty much done, and then we'll get into our topic today. So attendance is up to date. Homework 8.4, as I last checked, was still being graded. The solutions posted though, and homework 8.5 was due today. I did submit your grade reports for project 2, for the submittal 2. In the end, I think everybody did very well. Hopefully, of the projects that you will have in various courses in your college career, that wasn't the most work, wasn't the least work, somewhere in the middle. And I hope it was also pretty clear to see, like, from point A to point B. Those projects that like don't seem to end are the ones that always kind of bugged me when I was a student. All right, I'm going to talk a little bit about this. If you've had me for class before, you know about the at-home game, but I'm going to talk about it today for those of you that never had me for class before, so you'll know what that is. But I'm going to talk about the remaining housekeeping for the class first, okay? So when I say remaining housekeeping, I'm talking about the grade that you're going to get at the end of the semester. So attendance. We have 3 more lectures remaining, but everything up until now is up to date. So you pretty much know your attendance grade, other than the fact it'll get adjusted a little bit between now and the end. The analysis project, that's done, okay? And the first 2 exams, they are graded, okay? What about homework, okay? As for right now, everything up to 8.3 has been graded, 8.4 is being graded, 8.5 is due today. We have 2 more homework assignments. We have the homework that I'm assigning today, which is due Wednesday. This is on aids for structural analysis. You'll know what I mean about that when we get into the lecture today. Then we have a final homework on tributary area. Now that's going to be due on Friday. One thing about that homework, because we have our final on Monday, I'm giving you the solution to that homework right at 10 a.m. on Friday. So for homework 9.2, I'm not going to accept anything late because I'm giving you the solution right when it's due. And I want to give you the solution so that you have it for study for the exam on Monday. So that's why I'm not accepting anything late. I do have one bonus assignment, and that's to do the course eval. I genuinely take the feedback pretty seriously, and I want you to do it. You could say I'm the worst professor ever, but I do want you to do the survey. If you do the survey and upload proof that you have done it, I will add 10 bonus homework points on your homework average. I don't want to see what you wrote in any way, shape, or form. I just want to see that you did it. So if you go on the course eval and just upload a picture of your completed survey list or what have you, that's all I need. And that begs the question, can you get a homework average over 100%? Yes, I don't have a problem with that. So yeah. All right. Remaining lectures. So today we're going to talk about aids for structural analysis. Wednesday we're going to talk about tributary area. We've already talked about that a little bit in relation to the project. We're going to be a little more formal about it. Really the theme of this week is the real world. That's sort of the theme for this week, is real life. And then we're going to have our exam review, okay? For the exam is going to be on Monday. It is from 10:15 to 12:15. I have an exam from 8 to 10 on Monday as well. So I'm going to be running from Corbly over here. Excuse me. So I'm going to be running from Corbly over here. So we're going to start right at 10:15. I'll tell you, I'm not designing this exam to be any longer than the other 2. This exam is going to be designed to be 50 minutes long. So if I would wager, a lot of you will finish early. I've given a similar exam in the past, and usually after the first hour and a half, those people are gone. Of course, I'm going to give you the full 2 hours, but this is definitely not going to be a time cruncher. What's on the exam? It's not comprehensive. It's influence lines, masthead, and what we're talking about this week. That's the final, okay? And what we're talking about this week is not super inherently new. It's just sort of packaging a lot of the stuff that we've done this semester into a little bit of a different form, but you'll kind of get the gist of what I'm talking about after today. I am going to do the CLO survey during the exam, where you rank the student outcomes and whatnot, but that you'll have plenty of time to do that during the exam. Sound good? All right. With that, let's get into aids for structural analysis. You're probably like, what are you talking about? There's aids that we could have used this whole semester? Well, no, but there's aids that you can use next semester. And so what I'm talking about with this lecture are what I would call formulas for common loadings. Sometimes we call those aids for structural analysis. If you go to Google and you search shears, moments, and deflections, you will probably find these in various forms. You will find some of these probably in your FE reference manual. Actually, I know you'll find some of them in your FE reference manual. But let's talk about what they are, okay? And particularly, I want to talk about how to use them, and I want to talk about some things to watch out for when you do use them, okay? Now, to set the stage, I want to look at this, okay? These are two problems that we did this semester. We did these problems, okay? We were drawing shear and moment diagrams for them specifically, okay? Now, the reason that I do this is because take a look at these. These are some involved problems. We've got concentrated moments, triangular loads, hinges, you name it, okay? These problems each contain components that you will have to deal with in the real world. We've seen how you need to understand how to deal with concentrated moments in order to apply virtual work to determine rotations in beams. You do have to deal with triangular loads for things like hydrostatic effects and things like snow. But I'm just going to be frank with you. You are not going to deal with these in the real world. You're just not. I'd love to be able to tell you that you were, but these are not representative of bread and butter analyses that engineers perform on the regular. This is not normal. It just isn't, okay? That's normal. It is. That's a normal beam that an engineer might need to deal with. Now, I want to take a look at these two beams, okay? So the beam on the left is a cantilever beam that's 3 kips per foot, that has 3 kips per foot on it, distributed over its length, and is 25 feet long. Now the beam on the right is 37 feet long, and it has a distributed load of 1.95 kips per foot over its length. Is there really any difference between these two problems? Really? No. You might say that the only difference between these two are the values of their system parameters. Sorry, I was waiting for the little smirks. So that's the truth. I mean, really, it's just the only differences between these two problems are their numerical inputs. Structural engineers might have to deal with these problems, very routinely. Simply supported beams with uniformly distributed loads. The only thing that changes are the lengths of the beam and the loads. But the scenario is the same. Instead of having to analyze this beam over and over and over again, why don't we develop some formulas or some analysis aids to handle these routine computations? Something like this, okay? This is a screenshot from the spec that's published by the American Wood Council. So you'll find this in one of the design aids for timber design. And here we have a cantilever beam, uniformly distributed load. Let's take a look at what we find here. Okay, so here's the scenario. Okay, cantilever beam, uniformly distributed load. So what do we know? Okay, here's the shear diagram. The shear diagram is linear. Here's the moment diagram. Moment diagram is parabolic. The maximum shear is W times L. The maximum moment is WL squared over 2. We know that the maximum deflection here is WL to the 4th over 8 EI. I can even tell you the deflection as a function of X. I can tell you the deflection anywhere as W over 24 EI times this expression here. I can tell you the shear at any point along the span. I can tell you the moment at any point along the span. Okay? So instead of having to re-solve this problem over and over and over again, just plug into this. It's done. There's nothing else to do. Okay? Now, one of the things I'll tell you is that these analysis aids that you find, they are blind to unit systems. Okay? So the idea is that your unit input will result in a comparable unit output. Okay? So if you put in feet for your length and kips for your load, you will get kip feet as a moment. Okay? Where it gets tricky is deflections. Okay? So with deflections, you need to either incorporate 1728 or you need to convert everything to a consistent unit system as an input. Either one's fine, but the formulas are not going to incorporate a unit conversion factor. So you need to be aware of that. Now, you need to be careful when using the aids to make sure that what you're inputting actually matches what you intend to input. So, for example, this is for a beam that's a simply supported beam, and it has a triangular load on it, okay? And if you look here, here's the formula for shear, for Mmax, for the reactions, for the deflection, and so on and so forth, and you see this term W, okay? Now, to be clear, W in this case is not 2.5 kips per foot. W is the total amount of load. So W would be the area of this triangle. So 1/2 base times height, or 50 kips. So if you started plugging in 2.5 with this formula, you get the wrong answer. Okay? W is the total amount of loads. You got to be a little careful depending upon how they're formatted. Like if I was generating this aid, I would probably write everything in terms of this value, not in terms of the total load. Because personally, I've always thought that's a little confusing. But that's me. Other folks who write the steel manual think otherwise, and that's fine too. It's just different strokes, and that's totally fine. Now, another thing that you've got to be careful about is when you're adding terms from multiple analysis aids. And what I'm talking about is superposition, okay? So let's take this beam right here. So this is a simply supported beam, and it has 2 loads on it. It has a uniformly distributed load of 1.3 kips per foot. And so here's this. I can look up its Mmax formula, and it's WL squared over 8. Excuse me. Now, that WL squared over 8 occurs at the middle, okay? Now, what about the 17 kips? I can add that, and I can say, all right, let's determine its Mmax. And its Mmax is computed like this, PAB over L, where A and B are these 2 lengths right here. So it'd be 17 kips times 15 times 25 over 40, but that Mmax occurs there. So you can't just take this value and this value and just add them up. It is a common mistake I see engineering students do, and that's wrong. Because those maximum points on the moment diagram are not at the same place along the span. So in order to do that, what you can do is, instead of adding Mmax and Mmax, what you would do is go to the analysis aid and actually add the function. Add the function, and then you could do it one of 2 ways. You can either differentiate, solve for X, and plug in, or probably just do what I do, which would be just like plot it in Excel. Just plot, this moment diagram, plot this moment diagram, sum them up, and find where the maximum moment is and use that. That's fine too. Just don't take this Mmax and add it to that Mmax, because they are not in the same spot. Does that make sense? Everybody okay with that? So to explain how these work, I want to derive the analysis aids for that beam. That beam is the same one that we looked at before. And so I want to look at the reactions, the shears, the moments, and the deflections if time permits. And we are going to get the same answer that we're getting right here. So I want you to understand where these come from. If you take me for steel design, we're going to use some of these near the end of the semester. So I want you to see where they're coming from. All right. So let's see. So what we're going to do is we're going to derive formulas for each of these components. Let's start off with the reactions, okay? Nope, let's not do that. Put that over here. this like we do any other problem in structural analysis, only instead it's just a little bit more alphabet soup. So what do? We take that distributed load, we collapse that into a point load. What's the magnitude of that point load?
WL.
There you go. WL. We're going to have two reactions. We're going to have a vertical reaction, which we'll call RV. We're going to have a moment reaction, which we'll call RM. Nothing special about those terms, I just sort of made them up. So let's sum forces in the y direction. So we have WL going down, RV going up. Pretty simple. What about moments? Let's sum moments. And what I'm going to do is I'm going to say we're going to sum moments at the support. So if I'm summing moments at the support, I do not need to consider RV, but I do need to consider RM. Okay? And then what do I have? I have WL times a moment arm. What is the moment arm between the support and that idealized concentrated force? L over 2. So RM, sorry, that's not a subscript. I wrote that like it was a subscript. So we have WL times L over 2, so that's going to be WL squared over 2. There we go. So let's just put these up here for reference. Good Lord, that is a drum. There's two of them figured out. So that might seem very elementary, and it is, but we never have to use statics anymore to determine the reactions for a beam like this. Just plug and chug. Done. Okay? Let's take shear and moment diagrams, and I kind of drew a line here, and you'll see why. Okay? All right. Let's start off with the shear diagram. And notice I'm not even going to worry about units because we don't even care what units we're talking about with this. It could be SI, it could be US, it doesn't matter. Okay? How do we draw a shear diagram? Start at 0, hopefully end at 0. And so what do we find? A distributed load acting downward, a constant load causes a linear shear diagram. So we linearly decrease downward to minus WL, and then the reaction RV brings us back up to 0. How do we draw the moment diagram? We integrate this. What is the area of this triangle? 1/2 of L times this. Excuse me. our moment diagram starts 0. Excuse me. Linear shear diagram turns into parabolic moment diagram. Little to a lot, we go to minus WL squared over 2. That jumps up. So how do we determine functions? Like, how do we take this, we say, okay, what's v of x? What's m of x? How do we do that? Well, how do we determine functions for shear and moment anyways? We break out the secret weapon of structural engineering, which is a samurai sword, or a lightsaber if we happen to be a sci-fi fan. So that also means we need to define a coordinate system. Remember, if we're doing virtual work or we're defining coordinate systems, it's always easier to define the coordinate system at the free end as opposed to the fixed end. So we'll say this is our origin, so that's the y-axis, that's the x-axis, and we'll cut an arbitrary section at some distance x from the origin. So we're going to cut a section right here where this dimension is x. And we're going to cut a section, and we're going to look to the left. Section 1-1, looking left. So this is going to be, excuse me, that's going to be our shear. That's going to be our moment. Sorry. This is still going to be at a magnitude W. That distance is X. Excuse me. So, take this, collapse it into a point load. How much is that point load, by the way? Say it again.
WX.
WX. And then that moment arm from the section cut. It's not L over 2.
X over 2.
It's X over 2. So, let's see. Let sum forces in the Y direction. So what do we got? We got WX going down. We got V going down. Interesting. So 0 equals V plus WX. So therefore, V is minus WX. So V of X is minus WX. Does that comport? Well, here's our shear diagram. Every value on the shear diagram is negative. So our function is negative. It's almost like that makes sense or something. Let's scooch that over a little bit. How about summing moments at the cut? So what do we got? We got moment going this way. We've got WX times X over 2 going this way. So, W over 2x squared. Okay. Now, before we move on, and I want to say, this part I did kind of fast, I'll admit. But I did it fast because we've done this stuff before, and there's nothing here that's really different. It's just a little bit of alphabet soup. The alphabet soup's going to jump up in severity here in a bit, so we'll take our time with it. But let's take a look at these functions. Can somebody tell me something about these two functions that gives you a little bit of comfort that they're right? What's the relationship between these two functions? What's that?
Both negative.
Well, they're both negative. That's one. Okay, so that actually is a good observation because both the shear and the moment diagram were negative when we plotted them graphically. So that's right. I'm thinking of something else.
Derivative.
The derivative. What is the derivative of this? It's that. We know that the derivative of moment is shear. If I differentiate this function, I get 2x times w over 2, so the 2's cancel and I get wx, or negative, I should say. Let's also look at a further smell test. What happens if I plug in x equals 0 to either of these functions? And isn't that what we got over here at the beginning? Now what happens if you plot in x equals L? What do you get? What do you get for the shear function? You get that. What about when you plot in x equals L to the moment function? You get that. So I think by observation, we could say that B max is minus WL minus WL squared over 2. So as an engineer, we got that figured out. Solved. Let me stop for a sec. Because I did a lot just now, so let's stop for a sec. Does anybody have any questions about this so far? Now let's have some fun. Now let's look at deflections. Now, where do you think this beam is going to deflect the most? Let me scroll up, put this in context. Here's the beam. Where do you think the maximum deflection is going to occur? Say it again. Like, is it going to deflect the most in the middle?
The whole distance L away from the support.
Over here, that's the maximum deflection, right? So as an engineer, maybe I'd be interested in developing a formula that I can compute the deflection right there at any time. How do I do that? Well, let's see. Our trusty friend, method of virtual work. So I need the real structure. How many functions do I need to define these moments? Well, just one. I think I already figured that out. There's your moment function. What about the virtual structure? So the virtual structure place a unit load right here, because that's where we think maximum deflection is going to occur, right? Right? This dimension, oh, I need to put an L. Okay, so cut a section. Real and virtual, or the virtual shears and moments, I should say. Sorry. Bronchitis is not fun. All right. So, we have 1 times x, and then our virtual moment function, both rotating this 3-body diagram that way. Excuse me. Well, that's got to be familiar, doing that stuff. I love this topic, and I love doing it at the end, because not only is it a nice informal review of everything we've been doing this semester, but there's a tangible benefit that we never have to analyze this problem ever again, because the formulas are figured out. How do we figure out the formula? Well, we have a virtual moment function. We have a real moment function. So, break out the method of virtual work. So, since we only have one set of functions, we can say that the maximum deflection at the free end is just going to be the integral from 0 to L of m times m over ei dx. No summation of integrals necessary, because there's only 1 and 1. So, help me out. Little m is negative x. Big M is minus w over 2x squared. So from these, what is their product? Making y'all wake up this morning.
WX cubed over 2.
There you go. Positive so, now I should note, and I didn't put this here, although I did in the problem statement. We are assuming EI is constant, which just about every single analysis aid I've ever seen does, except for when it's like explicitly stating that it's not, and those are a little more difficult to find. Most of the common analysis aids that engineers are going to deal with assumes that EI is constant. So, therefore, so what do we got? We've got 1 over EI times W over 2x to the third dx, right? Because it's mm over EI, so EI is on the denominator, and that's our little m big M dx. Now I remember my Calculus 1 teacher told me that anything that's a constant I can factor out of the integral. Is 2 a constant? Is EI a constant? Yes! We're assuming it's constant. Is W a constant? Yeah, W is the 3 kips per foot, or 1.95 kips per foot. Of course it's a constant. So, now that's an integral that even I can do. What is the integral of x to the third? I believe that's x to the fourth, bless you, over 4, evaluated from 0 to L. Fundamental theorem of calculus states I plug in the top number minus plug in the bottom number. So minus 0. So I think that, let me see, is that WL to the fourth over 8 EI? Did I do that right? Huh. Let's put that up here. And I guess we should be formal about it by saying that that's deflecting downward. You know, I'll tell you what, just to make sure that we're not flying too close to the sun and then our wings aren't melting, are we off track in any way? Let's see. What do we get for our vertical reaction? WL? WL. What do we get for shear as a function of x? Wx. Now they say it's positive here. They don't bother with the positive and negative, but they do plot it the correct way. So that's fine. What about M max? WL squared over 2, WL squared over 2. Again, they don't bother with the sign. I like to keep it there, but that's fine. Deflection max at the free end. WL to the fourth over 8 EI. WL to the fourth over 8 EI. Well, by golly gosh gee, look at that. Now, something you might be wondering about is how in the heck did they do this? Well, let's see. Let's see how they did that. So, what we just did is a specific case of deflection. Let's do a general case. And I'm going to tell you, this is going to get messy from an alphabet soup. issue. So I'm going to show you how we're going to do this. So for the real structure, so to be clear, we're still using this. We're still doing that. Okay? That we're still doing. We're still able to use the real structure, which is we're still able to do that. Okay? Now what about the virtual structure? Okay. Now, I'm going to show you Dr. Mike's tip and trick on how to do this. This is the trick that I've always used. Okay? And I'll explain why. I want to place a unit load that is some distance A from the free end. Okay? I'm not saying X away from the free end, I'm saying A away from the free end. The reason that I'm doing that is because I'm going to do a lot of integration, and I want X to be my integration variable. A is where I want to find the deflection. And so I use a different letter to make sure that I'm not mixing the two up. Because if you use the same letter, it'll get real confusing when you start doing your integration. So my virtual structure is going to look like this. Okay? This dimension is A, and this dimension is L minus A. Okay? And so I have a vertical reaction here of 1.0, and then my moment reaction ends up being L minus A. Okay? I'm not going to make you do all these statical calculations right here, but I think based on what we've done with the theory of influence lines and what have you, I think you'll find this is pretty easy to follow, right? Because we'll have a shear diagram that here's 0 minus 1 over to minus 1, jumps back up to 0. The area of that region is just that rectangle, but negative since it drops downward. And then the moment diagram maybe I should use the small letters there. This is so that's 0 down to negative L minus A, brings that back up to 0. And so we're actually going to have two functions. We're going to have a function here and a function there. Now, M1 is 0, and that is valid from x equals 0 to x equals a. But then we're going to have another moment function which equals something, and it's going to be valid from x equals a to x equals L. And how do you find that second moment function? Well, that point is a comma 0. That point right there is L comma, and I guess what we'll do is we'll say negative L minus A. We know that the slope of this line is what? What is the slope of that line? You don't need to do any math. It's -1 because that's the value of the shear diagram. So we can use point slope formula, y minus y1 equals the slope times x minus x1, and you end up getting a minus x. That's what you end up getting. And we can go through that if you'd like. Here, we'll do it over here real quick. So we'll do it like this.
Excuse me.
Bless you.
Thank you.
So not very challenging. Just use that point and that slope. So in order to determine the deflection at any point, so here's how we're going to have to do it. So remember, the method of virtual work is to sum all of the integrals. Well, now we're going to have two of them. We're going to have one integral from 0 to a of m1m over ei dx plus another integral from a to l of m2m over ei dx. But what's going to happen with that first integral? What's going to happen with this first one? What is m1? 0, right? So because this is 0, I'm integrating 0, that whole integral can be ignored. This whole integral goes to 0. And I should say, m1 is 0. So that's why. So this equals one over ei, little m, big M, that's the integral. Again, I know it's alphabet soup. I'm sorry. I can't do anything about that. I can't make the alphabet soup go away, but I can calm it a little bit by factoring that out. And doing that. Or this. Now, that is an integral that you all should be able to do by hand. It's going to take a little bit of math, I know, but we have the integral of a times what? X squared, which is x cubed over 3, minus x cubed over 4. Plug in the top number, minus plug in the bottom number. That's supposed to be a. I don't know why that was written as 0. It's supposed to be a. And so when you chug that integral out, you get, and you all can do it on the side, but when you do that, what you get is 1/3 AL cubed minus 1/4 AL to the 4th minus 1/12 A to the 4th. Like that's what you get when you chug that out. So you get the deflection at A is minus W over 2EI, and you get 1/3 AL to the 3rd minus 1/4 AL to the 4th minus 1/12 A to the 4th. And so that'll tell you the deflection at any point. Now, how does this compare with what we had previously done? How does this compare? Or sorry, not with what we had previously done. How does this compare with our analysis aid? Okay, so here's our analysis aid. Let's see what they did. Okay, so the first thing that you'll notice is they factored out the denominators. Okay, and so what they did is they divided everything by 12, essentially, so they turned this into, or made everything to have a 24 denominator. So this one right here, instead of 1/3, maybe that's, or no, sorry, this one right here. This one's like 2 over 24, and so on and so forth. So they just did a little bit of algebra to simplify that out. I can carry that out if you'd like. Let's go ahead and do that. Well, we're running out of time, so I don't have time. Basically what they do is they multiply all that through and then carry that through. I'll do that on the calculation right down here, but I'll go ahead and let you all go. Let me pull up the code real quick, and then for anybody that didn't get the code, I'll fill in the rest of this deflection calculation for your notes, and I will see you all on Wednesday.